Hello, everyone. Today we're going to solve the Leet code question, remove element. For this question, let's see what it's asking us. So we're given in a vector of nums, so vector of integers, I should say, and we're also given a key. So I know it says val, but just think of it as a key, and we want to remove all occurrences of that key inside of our vector. The relative order of the elements may be changed, so we don't have to, have it persist in a particular order. And then additionally, what we want to do is we want to return the number of values of non-key elements. We'll talk about what that means, but essentially we could see here in this example list, our key is 3, right? And we have 4 values in total. So how many are not keys? 2 of them. These 2 twos, actually that's kind of unfortunate phrasing. These 2 twos are going to be our return value because these are the 2 non-key values. And you can see the 2 non-key values get placed on the left, and then the other values just get placed on the right. And there's no particular order the non-key values have to be in. So you could take a look at this case. It'll make a little bit more sense here. By the way, we're doing all of this in place. So we'll get to a little bit more about what that means, but just know we're using kind of like the same vector. So here we have I think these 8 elements, and we have a key of 2. So you can notice that our keys are going to be placed. Oh no, actually we have a key of 2, but we have 3 of them. We have 2, 2, and then this last 2 over here. They're going to be stuck on the right, what I call the key buffer. So we're going to go ahead and put them on the right-hand side. Once again, I'm just going to use a little bit of this terminology called like a key buffer. It's not really a thing. It's just kind of terminology that I'll be throwing around in there. And then on the left-hand side, these are the non-key values. These are the values that are not equal to what our key is currently, which is 2. And notice there's no particular order for them. They don't have to be sorted or anything like that, or they don't have to retain what their typical order would be. But there is a kind of a pattern to this. What I do want to say about this problem is that it seems initially straightforward, just kind of removing elements from a list, given kind of a key, right? So it looks like, let's go ahead and just shift them to the left, and then everything else will just shift it to the right. Doesn't seem too difficult, and it's really not under these 2 conditions. So under either or for these 2. So what I mean by that is if we were doing a time complexity of O of n squared, or if we had a space complexity of O of n, this problem would be pretty I think pretty easy, pretty trivial, to be honest. For example, if it was O of n squared, how could we solve this problem? Well, all we needed to do is we could take like a bubble sort approach to this. We would have our nested for loops, and we would iterate through each of these elements. And for each time we found a key, or for each time we found a key value. So in this case, we found a key, we would go ahead and bubble sort it, push it all the way to the right. And then this is not a key value, so we don't have to bubble sort it. This is not a key value, so we wouldn't have to bubble sort it. And then this value, we would have to bubble sort it. And just like that, it would go ahead and get sorted out. So that one's going to be very, very straightforward. Another straightforward approach is if we could have additional space. So for example, let's say in this case, we know that there's going to be 3 keys inside of here, these 2s and this 2 as well. We could just go ahead and iterate through the list once. So time complexity O of n, so just one pass over. And all we need to do is we need to say, if we find a key, just go ahead and keep track of that index in a separate vector. So in a separate vector, keep track of all the key indices. So keep track of those. And then what we're going to do, or actually to make it even simpler, keep track of all the non-key indices. So keep track of all of these non-keys, right? So this one as well, or no, yeah, this one as well, the 0 as well. So keep track of all the non-keys in a separate vector. So keep track of those indices. And then what you'll go ahead and do is, once you're done with that passover, for all the non-key indices, get their corresponding elements, and then make sure to put them at the front of this original vector, right? So just go ahead and transfer them to the left. And then for the right side, we don't really care what it is. It's supposed to be all keys, and we can go ahead and just, if we made any mistakes there, we could go ahead and just populate it with keys. That's pretty straightforward. But you can see that if we were to use any of these 2 kind of approaches, The problem's pretty straightforward. There's really no issue with it. The issue comes when we're trying to modify this in place so we're using constant memory. We're not allowed to use an extra vector. And then of course we want to optimize our time complexity. So we want to use O of n, or big O of n, I should say. So that's what this approach is. I'll be honest, while kind of performing this problem, I did have to kind of perform a number of different trial and errors. I kind of was making my way towards the right approach initially, except I didn't consider a number of different edge cases that would come up and that were clearly observed when some of my test cases would fail. So some examples are like, what if your vector is full of all keys? So you have no non-key elements. So they're all keys. What do you do in those instances? My logic would fail. Or what if you had just one non-key and all the rest of them were keys? It turns out you would also, or in my instance, I would get into some issues as well. So bit of trouble. I won't pretend that I was able to kind of go through this problem in a very straightforward manner with this constraint. So let's go ahead, and what we're going to do is a little bit different from what we would normally do. And that's that, let's go ahead and take a look at this at a high level, then review the code. And then afterwards, we're going to apply this code logic to a test case, specifically this test case, and then see if it makes sense. Once again, the reason I'm doing it this way is just because I'm not that actually confident that I would be able to kind of explain all the different edge cases within my typical solution without kind of making it a little bit confusing. So what I'd rather do is I just kind of rather go through the solution, let you know why I put certain things inside of there, and then that way it's a little bit more coherent. Okay, so let's go ahead and go through these problems. So what we're going to do is let's examine the first test case. So what we want to do is we want to iterate through technically all of the values, but not necessarily. We want to just iterate through all of the values while we haven't reached the buffer at the end. And initially the buffer at the end is going to be 0. So there's nothing that we've kind of swapped or stored at the very end. There's no keys that we've stored at the very end. So this is kind of like a non-issue, but let's go ahead and iterate through this list. You can see that the first value that I encounter is going to be a key. So what I would want to do is, according to our output, I would want to stick this 3 at the very end. The only issue is there's already a 3 at the end as well. So I want to stick this key at the end, but there's already a key at the last index. So what are we going to do here? We wouldn't want to necessarily swap them because then it would have no effect. So whenever we find a key as we're iterating forward, we want to check, is the place that I would normally want to, is the index where I would normally want to place my key buffer, is that itself filled with a key? If it is, so while it keeps being a key value, what we're going to do is we're going to note it as a key and then shift over to the left. So this is going to be the next key buffer that I would hopefully want to be able to swap with. And it does work. So I can go ahead and swap this 2 with this 3. So this 2 gets placed here, this 3 gets placed here. And just like that, we're now in ordered position. Whenever you're done making the swap, go ahead and say that you went ahead and found that key. So now we know we found 2 keys. We found this key on accident, and we found this key on purpose. And we essentially want to stop before we get to the buffer. So that's kind of a little bit of approach there. It sounds a little bit confusing, but let's see if it makes a bit more sense here. So initially, once again, the place where I would put my first key would be here. But let's start from the left. Let's start iterating. So you can see my first element is 0. This is not a key value. So there's really nothing exciting when it's not a key value. So I'm just going to go ahead and continue to the next element. Here's a 1. There's nothing exciting about this because it's not a key. Here I have a 2. Now this 2, I want to go ahead and stick it in at the last index. But once again, I already have the 2 here. So what I'm going to do is I'm going to say, okay, so this is a a key, I'm going to recognize it. So I'm going to go ahead and increment the count right here. Say, that's not a good place to put it. So I'm going to try to use the 4. And I'm going to go ahead and use the 4. So it'll go ahead and swap the 4 and the 2. Or sorry, it'll swap the 4 and this 2. So you can see how it becomes 0, 1, 4. So that looks good so far. The next place that I can consider is the 2. This next 2, I want to go ahead and swap it into the next position, which is this 0. Remember, we've already considered this 2 and this 4 as part of the key buffer. The next part of the key buffer is going to be the 0. So this 2 is going to switch with the 0, and that's why it goes 0, 1, 4, 0. So because they get switched. And then with the 3, well, we don't really do anything with the 3 because it's not a key. So that's fine. And then we've already established that the last 3 values were part of the key buffer. We don't want to go into the key buffer, and we're done there. So it's hopefully makes a little bit more sense when we kind of see it at that high level. We'll actually go through it in much more detail at the very, very end of the video. But let's go ahead and continue. So now let's look at our solution. We can see here that we have a constant, and this is when specifically all of our elements are keys. So when all of your elements are keys, how many non-keys do you have? 0, right? So if all of your elements are keys, then we have 0 non-keys, right? So like you could imagine that in this example, if these were all 2s, we wouldn't return a 5 anymore because there wouldn't be 5 non-keys, there would be 0 non-keys. So that's going to be for an edge case. The next thing we want to consider is being able to keep track of how many values we found, how many keys we found. So maybe instead of found values, I should have put found keys. And then I also like to keep track of the last index. So this is just, I don't know, just for convenience, to be honest, because I could just have that written out, but I just feel like this is a little bit lengthy and it can get pretty confusing if we have a lot of things going on in a single line. So just for convenience, I wrote it out this way. Now, when do we want to iterate? We want to continue iterating until we reach the end buffer with the key stored. So remember, we don't want to go ahead and kind of get into the grounds of the key buffer, just because if you do get into the grounds of the key buffer, well, those keys have already been counted. If they're in the buffer, that means we've already counted those keys. So why would we want to go ahead and perform any logic with them? That's going to lead to double counting. So that's why what we have is we start at index 0 and we go ahead and continue until we get to the last index minus found values. Remember, found values is initialized to 0, meaning that this is going to continue all the way to the last index, assuming we find no keys. So it's going to go from index 0 to the last index, assuming that you find no keys. But as you find keys and you fill that buffer, then what we're going to do is we're going to stop short. And so I hope that makes sense. Feel free to kind of rewatch that section to see if it makes sense, but I'll just go ahead and repeat it once more. So we're going to start at the beginning, and we could ideally go up to the last index. However, as we find keys, then we're going to put them in our buffer, and we don't want to go to that part of the buffer. So notice while we do start at 0, we're going to go ahead and stop short as we find more and more keys. So let's go ahead and continue to the next part. Remember, if our current element is not a key value, so if it's not a key value, so this is val, it just refers to key. If it's not a key, then we don't really care about it. Notice the only condition that we care about is if you do find a key. So if you find a key, then we'll perform this kind of extra bit of logic. And so I do apologize. I know it's kind of like kind of a bigger block of code. It's not as pretty or maintainable, but so once again, we only care about if you find a key. The next thing is what we want to do is we want to say, okay, so what happens in the issue, or what happens when the place where I would want to put my key into the key buffer is itself a key. So notice, while the place where I would put my key buffer is a key, what do we want to do? We want to recognize that we found a key. So if I go ahead and go to the end value, so like we did in this instance, so I found this first key and I wanted to put it at the end, but it turns out it was a key. Well, that's kind of a bit of an issue. So we want to go ahead and increment the count so that we can move our buffer over to the left, right? So that's that's why we're performing this logic. We're performing this logic if we have already keys inside of our buffer. And so we'll recognize those immediately before the current element that we were working on. The next thing that we want to consider is the specific edge case when we have all keys. So let's say, for example, if you had all keys. Well, the issue here is, let's say, for example, the first value I have is 2, and let's say my key is equal to 2. Key is equal to 2. Well, the first value, I want to go ahead and put it in the last index, but that's a key. So then I'll go ahead and increment the count, and then I'll move to this space. So as part of my key buffer, but that's a key. So I'll increment my count and then move to the next buffer, but that's a key as well. And then I go ahead and increment, but that's a key as well. And so you could see that there's only there's only 5 elements here. So it only goes from index 0 to 4, right? So we have to make sure that, if I get to a point where the number of keys that I find equals the size of my list, then I know that I only have keys inside of there. So I can immediately stop at that point, right, with that specific edge case and say, well, there's going to be no non-keys, right? So return 0, there are no non-keys. And I don't like this double negative, but essentially because they're all keys, none of them are not keys, right? Kind of don't really like that double negative, but that's okay. So that's for specifically for this edge case. That's why this if statement was kind of thrown in there. That was something that took me some time to kind of figure out. The next thing is, let's say once we get past this, so notice it's a while loop because it's going to consider the cases where you keep finding a key in the buffer. So you try the next buffer, you keep finding a key, you keep finding a key. So every time you acknowledge, you increment that count, you acknowledge that you found a key, and you go ahead and try to shift over your buffer. Let's see. So once you're able to successfully find a key buffer, or once you're almost successfully able to find a key buffer, we want to be sure of it. And the next thing we want to do is we want to be able to perform that swap. However, we have to guard it with an if statement. And that's because there is a situation where we run into this issue where let's say we have all let's say, for example, we have all keys except for one value. So this 3 is a non-key. We kind of run into this issue. Let's say if I had 2, 3, 2, 2, 2, 2, like this test case right here, you run into an issue where you want to swap a value with, like, let's say, for example, this 3, this initial 2. Let's go ahead and take a step back. So let's say our key is 2, and let's say this is my list. I'm going to start off with this 2, which is initially which is initially a key. So I'm going to go ahead and try to put it at this last space, but it doesn't work because that's a key in and of itself. So I'm going to try a next key buffer space. Nope. So I'm going to go to the next key buffer space. Nope. So then in this instance, I'm going to go ahead and see that I can go ahead and make that swap here. So 3, 2, and so that works without issue. But I want to go ahead and not perform swaps with the original value if I'm already within the key buffer. So if my current element or my current index is already within the key buffer space, then there's no need to perform a swap and potentially double count a value. So that's why there's this kind of guard statement here. So that's one other reason. That's one other reason why I was having difficulty with this problem. I didn't have this if statement, and so I was just, whenever I got to this point, I was going ahead and swapping values, and that would lead to some issues with double counting. So I hope that makes sense. But if you're not within the buffer, so to put it simply, if you're not within the buffer, you can go ahead and make that. If you're not within the key buffer, then you can swap your current key with, swap your current key with a value within the buffer, and then make that swap, and then go ahead and increment your count because you're not performing a double count at that point. I didn't say really that simply, but that's okay. And that's really the logic. So you continue performing this until you get through all the instances, or you get through all the values up to the key buffer, but not including the key buffer. So now that we found all of the keys, what we want to return is not the number of keys, which was another issue. I actually accidentally didn't read it thoroughly, and I just returned the number of key values, and I kind of had an issue there. But what it wants is the number of non-keys. And so in order to get the non-keys, it's just a simple subtraction. It's just the size of the list minus the number of found keys, right? So the rest of them are going to be non-keys, and just go ahead and return that value. And this is, once again, an in-place solution. Constant memory. It's a little bit complex, but for myself, I kind of found it a little bit complex just because of the different edge cases. But I hope that makes sense. Let's go through one last test case in detail to see if it makes sense. So here, what we're going to do is we're going to set up our problem specifically for this test case. So let's forget about the rest. So we're going to set up our key as 2 and initialize our found values to 0. Our last index is 7 because there's 8 elements. Here, we're going to start at the index. We're going to start at the index 0, and then our key buffer is going to be the last index because it's going to be last index minus found and found values. And we know that found values is set to 0. So that's what it is there. And also, I strongly recommend to use, if you feel more comfortable, you could also use the debugger within online GDB. Here it's a great tool to be able to kind of go through and have these initialized for you, so we don't have to kind of manually set these up. But I just thought for convenience, we'd go ahead and take a look at this test case in this manner. So what we're going to do is we're going to start with the first value 0, and we notice that it's not the key of 2, so we don't really have to do anything there. We're just going to go ahead and increment our index. So now we have index 1. We could see that the element there is not the same as the key value. So let's go ahead and increment it. So now we increment our counter. So now we're at index 2, and we can see that our element is the same as the key. So now this is where we kind of go into this logic. Since we did find a match, we ideally would want to put this at the end of our list. However, notice that at the end of our list, there is already a key as well. So here we have a matching 2. So what we want to do is we want to immediately acknowledge this key at the end. So we're acknowledging the last key. We're not acknowledging the first key yet. So we're acknowledging the last key. And whenever we find a value, that also updates this formula where our buffer is. So it's going to be 7 minus 1. So it's going to be 6 now, meaning that this is our key, the start of our key buffer, essentially. And can we perform that swap? Can we perform that swap? Yes, we can, just because we found a suitable candidate. So we're going to go ahead and make that swap here. So here's a 4, here's a 2. Looks good. And then now that we've performed that swap, we can go ahead and increment we can acknowledge that we found that key as well. So there we go. So that's our second key that we found. Now what we're going to do is, since we're done with that logic, then let's go ahead and go to the next, or increment our counter. So let's go to index 3. And at index 3, we can see that, let's see, actually, one thing I forgot to do is I forgot to also update. So whenever we modify our found values, we also should have modified this as well. The start of our key buffer, which is value 5. So the start of our key buffer is actually here at 0 now. Just wanted to kind of note that. So every time we change the found values, it also changes the start of our buffer. So anyways, going back to this. So at index 3, we can see that our element is 2, which is the same value as our key. So what we're going to do is we're going to try to, we're going to check our buffer space, and we're going to see, is this a key value? No, it's not. So perfect. And then also it's not within our key buffer. So then what we're going to do is, or our current element is not within our key buffer space. So what we're going to do is make that swap. So we're going to put a 0 here. Let's put a 2 here. And now that that's performed, we're going to acknowledge it. Now that we've performed the swap, let's acknowledge it by incrementing our found values. And once again, this also shifts our buffer to the value 4 now, 4. So notice we're going to continue. Just want to keep everyone's attention in terms of we're going to continue while our index is less than or equal to essentially this expression, the start of our buffer value. So here we're at index 0, 1, 2, 3, and now we're going to 4. So this is going to be our last iteration. So here we're at index 3. Here we're at index 0, 1, 2, 3, 4, index 4. Forgot to increment that. Here we're at index 4. We can see that the element is 3, so it's not a key. So we're not going to do anything there. We're going to increment our index one more time, and you can see that in this case we've kind of set our loop to false, so we got kicked out of here, and there's really not much anymore to do except go ahead and find our answer. So we know that there is a size of 8 to this list. We know that we found in total 3 keys. So the number of non-keys is going to be our size minus the number of found keys. So that's why our non-keys is going to be 5. And that's what we're going to return in this example, which is what we should be getting. I hope that made sense. I do appreciate you staying with me for this problem. As you can tell, I kind of struggled with it, but it is kind of a fun problem to kind of challenge yourself with. I hope that you're feeling comfortable as you're going through these video series and kind of trying them for yourselves. And feel free to comment if you also face similar struggles. Maybe you kind of tried it by yourself. But other than that, thank you so much for watching. I appreciate your time, and I hope to see you soon.